In the last video we made, let's say, a naive implementation of Metaballs, and this implementation, if you're working in 2D, it's quite easy to parallelize. You can run it on the GPU and it should be super fast, even with hundreds of Metaballs. However, I'm not sure it generalizes to 3D, so today we're going to look at a way to do Metaballs in 2D and 3D using something called merging squares in 2D, merging cubes in 3D. So before we get started, let's copy the old program and let's call it naive Metaballs, and then let's go in here. So the basic idea, and I will provide a link to this resource in the description, but the basic idea is that instead of evaluating the metaball field on every single pixel, we evaluate it on a grid. And then depending on the grid values in a given square, we draw certain lines or don't draw certain lines. And you can think of it like this: if you have a green square, it means that that point is above the threshold. So basically this thing should be inside the metaball and the other point should be outside. So if we know that this point is inside the metaball and the other ones are outside, where should the boundary of the metaball go? Well, we don't know for sure, but we can guess that it's somewhere like this, that you see. Let me zoom in. Something like this. If this is inside and these are outside, the line is probably somewhere, the boundary of the metaball is probably somewhere around here. And then there's a bunch of other cases. So for example, this one. If these two are inside and these two are outside, probably the boundary now goes like that, right? So let's start by implementing this, and then there is a further refinement you can do to make it look better. But let's try this one first. So now we need, like, let's say a width of the grid and the height of the grid, and that can be a lot lower than the actual screen size. So let's make them like this, and we are going to start out with two hard-coded balls like we did before. So I'm actually gonna nuke a lot of this. And let's clean out this one as well. And I think for the fall off, to begin with, let's keep these two. All right. So how do we update the field? Well, I think we should just loop over every point as before. Then we need to evaluate the field at that point. But now the question is, where are the balls? So let's reintroduce these, like ball 1. So we'll just have ball, well, let's also make a ball 2. And this one will place sort of off to the side to begin with. All right. So now what is the distance of this point to ball 1, let's say? And actually we want the distance squared. It is this. And then we can say field ji is just this simple fall off. And I suppose we can go ahead and do this. So this is ball 1, and this is ball 2. Okay. Let's not do those things. Let's not draw the texture just yet. But now we have, here to begin with, we have updated the field. Let's give it a new name. This one I'm going to get rid of. And this one too. And also this stuff in principle. But now let's copy this for loop, and then we are going to do a draw pixel, I think it's called. So let's draw a pixel at each of the points. And actually, what is the spacing? So spacing should be a width like that. The width divided by the number of grid points. And in principle, we should have one for x and y. So let's actually do that. And now here, if the field is greater than the threshold, we make a red pixel, and otherwise we do a black pixel. Let's see how that looks. And there is this thing which we should get rid of because I deleted the ball speed. Now we can't see anything because they are too small. So let's instead draw a rectangle, and I just let me see what the interface is. So actually let me just do it down here. So x, y, and what is the width? The width can be spacing, maybe divided by 5, something like that. Still, we don't see anything. Let's try as a baseline just to draw some red squares or blue squares, just to check that it's actually working, and it's not even working a little bit. Okay, so that now it's working. Yeah, so this is like, these are all the grid points. We don't, actually it's a bit more correct to do this. I think, so we have them on the edges, but then we need to make sure that this thing makes sense. Yeah, we need the spacing here as well. Copy that one. And then just ball 2 everywhere. And I think that is correct. Because we need the coordinate x and y coordinates of the grid point. So we need to remember to use this spacing. All right. So now let's try to draw these instead. Okay, this looks more correct. So you can see kind of you can feel that there is a ball here and a ball here. But now let's actually do the marching squares. So maybe we'll just do marching squares here, and all of those variables are global variables, so we don't need to pass them. Okay, so here we have the marching squares, and we want to go through each individual little square and do some calculations. So how are we going to do that? Well, it's almost this loop, but we don't want to go to the very edge. So actually we want to do this because we're kind of looking forward. Now the way you normally do it is you kind of construct a number based on the edges. So let's use this encoding. So we can kind of use this as a reference, this image as a reference. So we are in a given square now, and let's find the state, which starts at 0. And then we have to look in the lower left. So what is the lower left? That is the field ji, but actually we need to increase this by 1. Yeah, because I think y is going downwards. So let's try this. Then we need to check if it's greater than the threshold. And then we can actually make it let's do like this. Yeah, so this number, which we cast it to an integer, is either 0 or 1. And then if it's 1, we shift it 0 bits to the left, which means that it's just equal to 1. So hopefully this will make sense in a bit. So now let's check this one. So that is supposed to be the second bit. So that means we have to shift it by 1. Then we can go and check this one, which is supposed to be the third bit. And finally we check the original position, which is the fourth bit. So now we have this kind of thing. And let me do some more alignment like that. And probably I want to do this. Okay, so this is supposed to be lower left, this is supposed to be lower right, and this is supposed to be upper right, and this is upper left. So we kind of construct a state by looking at each corner, and then depending on the state, we're going to do different things. So did I mess it up? Somehow I messed it up. Okay. And again, we're going to refer to this table. Okay. So if the state is 0, it's this one. We don't do anything. If the case is 1, we need to do something. And why is it indenting weird? Please stop that. Okay, so we need to find this point and this point, and we need to draw a line between them. So actually we're going to need these things, and they kind of belong out here. So I can also remove them down here. Okay, so we need to find this point, which is in the middle between those two. So let's find first the upper left. Well, that's probably I times spacing x, upper left x, let's say. And here we want the y, and that's just j instead. And then we want the lower left, and that is simply +1. All right. And we can even do this. Now we want to draw a line between those. Well, now we have this point and we have this point. So we want actually the middle point is kind of like in between those two. So we can take the average, and the same thing with y. So I just have to replace x by y. And now we need the other point. So then we need the lower right and the lower right. And then we need x2, which is the average between lower left and lower right. So we do that. Let me fix this up. And then we just draw a line between those. And let's draw it as a red line. And then we need to break. So let's start with this and see if it even like works a little bit. Okay, so here you can see it is actually working. These dots are not fully centered, so that makes it look a little bit off, but I think it's correct. So you can see here we have like an upper right edge of the ball corresponding to this one, and we get a line like that. So now the rest of the implementation of this algorithm is just doing a bunch of cases like that. So I will do that off screen, and I'll see you in a little bit. All right, so now I've typed in all of these cases, and some of the cases are when you only draw the lines, they're identical. For example, 6 is the same as 9. I've kept them as separate cases because later on we might want to not just draw a line, but actually color in the part that should be colored in. So let's try to run it and see how it looks. So I think that's pretty good. Let's try to see that it also works. We're not doing that. We're actually running it every frame now, and you can see it's running at 60 FPS, which is good. So let's try to move a ball, but then we need to update the field if we do that. So let's try to also update the field every frame. And we need the ball speed, which can be, what did we say? 500 times the FPS, divided by the FPS. So still running at 60 FPS, but you can see I can move this around and kind of, it's continuously updating the boundary. Let's try to make it a little bit more coarse-grained, maybe 200, maybe that's too much, but actually not. You can see it's still 60 FPS, and we get this like much better looking thing here. So now I guess we don't really want this anymore. It's not doing anything. But okay. Still there's an issue. You can see it's very jagged. So we're gonna try to fix that. The way we fix it is by, instead of just guessing that it's midway in between, we're actually gonna look at the values and do a better estimate of where the edge should go. And we will do that by kind of linearly interpolating. So how exactly do we do that? I think I want to change this to float, and then let's have a look at this one. So actually let me just quickly check what the draw line, it takes integers, okay. But that doesn't matter, let's go back here. Okay, so how, where should the boundary actually be? So we're kind of gonna guess that we have a linear function between the 2 points. So what does that mean? That means that we have point 1, which has a value of x1, y1, and we have point 2, which has a value of f of x2, y2, and let's call those like z1 and z2. And then we need a line between those two. So what should that be? Should be, how does that line look? Well, we know that when, yeah, it's a little bit weird. Let's just call them T1 and T2. So we know when, so this is like Z is a function of T. When T is equal to T1, it should be equal to Z1. So let's do that as like the base. Then what is the deviation from T1? And basically when we're equal to T2, we should be Z2, and it should be a linear function between that. So we can actually do this thing that Copilot is suggesting, where we divide by the distance between the points and multiply by the function value difference. And that is good. So now we need to find what is T0, which is where z of T0 is equal to the threshold. And we find that by, let's write it like this. So we know we have threshold on the left-hand side, and then we just isolate T. So we need threshold minus Z1. Then we multiply by T2 minus T1. Then we divide by Z2 minus Z1. And then we add T1. Actually, T1 we can say is 0, and this we can say is 1. So we get a function like this. I think that looks correct. Then we know the fraction of distance. We have to go from Z1 to Z2. And that gives us a new x1 and y1 and a new x2 and y2. Okay. So let's actually try to write it out. So x1 should be let's have a t0 variable, which is threshold. And what is z1? Z1 could be the upper left, which is this. And then what is Z2? That is the lower left. So that's that. Except we need a +1. And then x1 is, and now we have to remember that we said that upper left was corresponding to 0. So we have to say upper left x plus this thing. Same thing with y. And then we have to repeat that for x2. And then we have to do it for all of these cases. So before we get too crazy with that, I think I'm actually gonna copy this function, because maybe it's nice to have as a reference. And this one will be the real one. And then we can revert the changes we made up here and turn things back into integers. Okay. Now I'm going to do this rewrite off screen again, and then I will see you on the other side. All right, so here we are. Now we do linear interpolation at each step, and I think it could be fun to have a switch where if we want to use interpolation, we do this one, and otherwise we'll use the old version. And then if we press like key I, then we toggle it. So let's see. It's running at 60 FPS still, which is pretty good. If I now go ahead and press I, you can see we changed the simple way of doing the interpolation. So clearly, like, it's a much better result, even though it's on the same grid. It's not like we increase the resolution or anything. It's just smarter way of estimating where the boundary is. So that's pretty much it. So one thing we could do now is, let's say, for example, case 15 is where everything is filled. So we could also just like draw a rectangle here, like that, and then we get something like this. Now the very inside is filled. We still have to handle these cases if we wanted to get it fully filled. But that's just to show you how easy it is to also fill it. But before we do that, I think we can try one thing, which is in the update function. Sorry. So here, instead of using the simple fall off, why don't we try to use the more complicated one, which completely destroyed the frame rate before. Now we're still running at 60 FPS, even though we're using a very complicated function to calculate where the ball is. And you can see it gives this very interesting shape. If I changed the bad mode, it's just arguably looks even more interesting. But anyway, so with this method, with the marching squares method, we get much better performance for basically equal results. Okay, one problem with this implementation is that there's a lot of copy-pasted code, which is what I did just to get it working. Essentially, this block is copy-pasted, this block, also with the draw line, in every single case. And the only thing that's changing is the values for these indices here. So I'm thinking maybe we can make a macro. And let's call it marching squares line. And then I kind of want to do like, yeah, if it were Lisp, I would do something like upper left, be a simple upper left to lower left. Let's not do that because it's gonna mess everything up. I would do something like this. That is one point, and then the other point I can see down here is lower left to lower right. Problem is we cannot really do that. Right, we cannot really do that. Cannot really do that. Okay, I think I have an idea. So what if these were macros as well? So we're gonna try to do some really crazy macro stuff now. Right, so basically define ms line. It's gonna take a couple of corners. And what is it going to do? I'm not gonna put those right now. Well, maybe I am. So we're gonna define a block, I think, just to keep everything nice and contained. And basically we want to calculate these middle points, I've called them. And now let's calculate one middle point. So then we're just going to write corner 1 now. And the trick is that, for example, upper left is going to be also a macro. And what it's going to do is basically this. And the same with the lower left. Yeah, except then we cannot use this this number here, because then we're going to have a conflict. So maybe it will take like a number, and then we're going to just put that number there. I'm not entirely sure that this will work, but let's try it. So, and then for the first test we also need lower right. So upper left is ij, lower left is j plus 1, and lower right is this thing, plus 1 plus 1. And then we're going to say, give me the first corner, where I call it index 1. Give me the second corner. I'm going to have to put all these in the end anyway, so let's not do it right now. Give me the second corner, and then I want to run all of this stuff. All right. Away with you. So this should calculate xm1 and ym1. Now I can do the same with 3 and 4. But that should calculate this, and then I can finally draw the line between those. Where does this belong? It goes up there, fair enough. So let's try this. But now let me just insert a backslash. Like that. And then I'm actually going to align those because it looks horrible. Okay. So I kind of think that should just work, but you never know. Let's try to run it. And it compiled and it's running and has the same. Okay, so that's pretty cool. Now we just need to define the other corners. There's only one left actually. So, sorry, it's not that one I have to change. It's this. And that just has a +1 here. Yeah, so the trick is kind of this thing where, let's say I say upper left 3, then the preprocessor, give me a second, the preprocessor will look at this expression and replace it with IDX x3. So the hashtag kind of means that take this variable and just append it to this variable name. So you can like do some metaprogramming where the variable names change. So I think that's pretty cool. Before we go too crazy though, let's implement this. So I commit this, and we will call it matching squares. Then we have that. Now we can do this thing. And now I have to go through all of these cases again, but you see now it's a lot simpler because this one uses the corners upper right with the lower right and lower right with lower left. So we can go ahead and delete that. Let's see that it still works. So much less repetition and much less room for error. So let me do that and I will see you back in 1 second. All right, here we are. Much simpler, and we're basically in each case we're just saying exactly what we want. There's no redundant information. Now, are these variables even used anymore? I don't think so. Let's try to comment them out. Let's see everything still works. So let's go ahead and delete those. Now we have very simple implementation, I would say. And even in these cases where there's 2 lines, I don't think we need those extra brackets, which is also nice. So let's get rid of those, and that's it. So I think that's it for this video, and I will leave you with something that looks slightly more interesting. Here we go. And that's it. And I will see you in the next one. Bye bye.